So we said in the last video that the limit of a function as x approaches a certain value, it's the y value your function was headed to, or like supposed to go to. So in this case, as x gets closer and closer to 2, if I think about walking along this function, at the place where x equals 2, I was expecting y to get to 2. And if I walk across the function from the other direction, same thing. I was expecting y to be 2 when I got to the place where x equals 2. Something different happened, but that doesn't matter. That doesn't change the limit. The limit is the place I was going to get. Here's the thing. We can only nail that value down if I was headed to the same place from both directions on the graph. So check out this picture, which is on your notes paper. Let's see how well I do here. Okay, so here we go. How about this picture? We said it doesn't really matter what happens, in this case, at C. So I'm not going to sweat what happens at C, but I want to know what was going to happen as I walked along the graph toward the place where C. So I'm walking. Oops. Walking. Looks like I was going to get to K. I didn't. There was a hole, but that's okay. But what if I walked from the other direction? Looks like my y was headed toward L. So now we have a problem, because if you ask me, and I walk from the left, what the limit is, I think the limit is K. Because somebody else who is walking from the right, what the limit is, they're going to say the limit is L. If we have two different answers, we have a very big problem. We love, as mathematicians, we love functions. We want to know there's one output for every input. So when the input is C, and I want to know what the limit of the function is, I can't have this situation where I have two different answers. So this is like the big idea in theorem 3. It's not that I need you to know what theorem number it was, but you're going to need to know this by heart. A function f only has a limit. We can only talk about what the limit is if the limit from one direction is the same as the limit from the other direction. So we need a notation now for this idea of finding the limit from one direction or the other. So you can see here, I've said in this case, the limit as x approaches c of f of x does not exist, because if you ask somebody who walks from the right and somebody who walks from the left, they get different answers. So here's the notation we use to start to discuss that. If I walked toward C from the from the left-hand edge of the graph, that's this one, and we indicate that I'm approaching C from the left hand by having this little negative sign up there. That is not to say that C was negative. That's to say that you were coming at C from numbers that were less than C. So I would read this: the limit as x approaches C from the left of f of x equals K. And this one I would read: the limit as x approaches C from the right of f of x equals L. And I refer to this as the right-hand limit, the limit of the function as you approach from the right-hand direction. I call this the left-hand limit, the limit as you approach from the left. So there's a place in your paper. Let's find that place. All right, so there's a place for you here to write in this notation and to write in sort of the two different versions of Theorem 3. One in symbols. Part of our job in Chapter 2 is to make sure we learn how to use limit notation, and then to kind of like describe it in words. So here's your slide to help you there. A function f of x has a limit as x approaches c if and only if the right hand and the left hand limit exists and are equal. When I say it has to exist, it doesn't mean that point has to be filled in, but the answer can't be infinity or something that's not a number. So in this case, K was some number, and I had a limit from the left, which was K. I had a limit from the right, which was L. They were both numbers, but they didn't match. So you can see this. You're going to make sure that you get the words version and the symbols version onto your paper. And then when you come to class tomorrow, you're going to check with your friends to make sure you got all the symbols right. You might have me check it too. It's your first time probably writing limit notation on your own, and it takes a lot of practice. So notice we have the variable x. We have an arrow pointing toward, so we say as x approaches. And then after that comes a number. In this case, c is the value. So I have c standing in for the number. The plus sign or negative sign that come after indicate whether you were approaching from the left or the right. And notice that's different from if you had a c that was negative. So you could say the limit as x approached -1 from the right. Just notice that that negative sign comes in front of the 1, so I know it's the one that's negative. It's this symbol that comes after that tells me whether I was approaching from the right or the left. In this case, the right. All right, so now I want to talk about this example down at the bottom of that page. We're going to talk about the limit as x approaches each of these, 4 numbers. I might have left 0 off my list. I'll check it. All right. So I have this function. It's piecewise. There's some holes in it, some jumps. So we have to figure out how to talk about the limits at each of these different x values. At the place where x equals 1, this is my notation for the left-hand limit. The limit as x approaches 1 from the left. All of this slide is about the place where x equals 1, which is here. So my left-hand limit is 0, because if I walked along the function from the left, the y value I was approaching was 0. The limit from the right is 1, because I was headed toward 1. So separately, there's a whole new different question, which is what is the output when the input is 1? Well, that's 1 because that was the dot that got colored in. Notice that this dot down here was open. And although this doesn't matter to the question of the limit, it's going to come up when we talk about continuity. I would say here the limit as x approaches 1 of f of x does not exist because the left-hand limit and the right-hand limit do not match. If I look at the next spot, the next interesting spot, when x equals 2, the limit as I approach 2 from the left is the y value at that open circle, which is 1. If I approach from the right, I end up arriving at that same open circle whose y coordinate is 1. It doesn't happen to be that that circle got colored in, so the function value is actually the place where that dot is, which is 2. But if you ask me if there's a limit, I say yes, the limit as x approaches 2 of f of x is 1, because the left-hand limit is 1 and the right-hand limit is 1, and they are equal. So catching on? If you look at 3, 3, at least there's no problem. There's nothing even to worry about. I approach the same spot from the left as I approach from the right, and that's up here, this y value of 2. I say the left-hand limit is 2. The right-hand limit is 2. Happens to also equal the function value. So I would say that the limit as x approaches 3 of f of x is 2. Remember that this part is not contributing to our decision about whether the limit exists and what that limit is. And then, did I put 4 in my slide set? Oh, here's 0, good. Okay, so now what about what about the endpoints? Don't want to freak you out too much. They're not going to... We have a technical definition. You might ask me what the left-hand limit is as x approaches 0. Well, as x approaches 0, there isn't even any function out there to walk on. Numbers to the left of 0 aren't even in the domain of this function, so I don't have to worry about giving an answer. It's not that the limit doesn't exist. It's like it doesn't even make sense to talk about. So you would say, no. But they're not going to ask you to find it when it doesn't even make sense to talk about. I can talk about the limit as x approaches 0 from the right, though, because I'd be walking along this function, and it looks like I'd be arriving at 1. 1 also happens to be colored in, the y-coordinate of the colored in point, so I say f of 0 is 1. And because the left-hand limit didn't make sense to talk about, I say it's okay to say that f has a limit as x approaches 0, because there's only one limit that makes sense to look at, and that's 1. Same thing at the other endpoint. I don't worry about what happens at the place where, I don't have to worry about the limit as x approaches 4 from the right, because I can't approach 4 from the right. There's nothing out here. This is just like empty space. So I say that the limit as x approaches 4 from the left is 1, because that's that y value. The limit as x approaches 4 from the right doesn't make sense to talk about, so we don't even go there. F of 4 is 1, because 1 is the y value of the colored in dot. And I say the limit as x approaches 4 of f of x is 1.